Picture this: a mysterious emerald visitor from beyond our solar system races past Mars at breakneck speed. Earth's most powerful telescopes, completely blind. NASA's websites, dark. And the only witnesses to this historic cosmic encounter are machines orbiting the red planet, scrambling to capture data that humanity might never see again. This is the story of 3I Atlas, the third confirmed interstellar object ever detected, and the unprecedented scientific scramble happening right now, 30 million kilometers from Earth, where no human eye can reach. On October 3, 2025, the universe played the ultimate cosmic joke on Earth's astronomers. Just as 3 Atlas swept closest to Mars, positioned a mere 0.2 astronomical units away. That's roughly 30 million kilometers. The Sun positioned itself directly between Earth and this alien traveler. From our perspective, the elongation angle, that crucial slice of sky separating the Sun from the comet, collapsed to under 10 degrees. For ground-based observatories, this isn't just inconvenient, it's a complete shutdown. Most telescopes refuse to point anywhere within 15 degrees of the Sun. It's too dangerous for their sensitive optics, too risky for their expensive sensors. And 3I Atlas didn't just dip into this danger zone for a night or two. It stayed there for nearly 6 weeks, from late September through early November. But here's where the geometry gets interesting. Mars sits offset in its orbit by more than 40 degrees. While Earth stared helplessly at a sun-blocked sky, Mars had a crystal-clear, unobstructed view. The angle between the Sun, 3I Atlas, and Mars remained broad, often greater than 50 degrees. For this brief, precious window of time, Mars became humanity's only watchtower, the solar system's sole vantage point for observing this interstellar enigma. When you're facing a once-in-a-lifetime cosmic event, there's no room for bureaucracy. Mission planners who normally work months ahead on carefully choreographed schedules had to throw out their playbooks. Standard protocols were set aside for emergency retargeting. Instruments designed to map Martian valleys and sample thin atmosphere were suddenly aimed at deep space. The pressure was relentless. Every orbital pass, every data downlink could be the last chance to catch something extraordinary. A sudden outburst, a morphological change, an anomaly that might never be seen again. There was no time for second guessing. Everything depended on the speed and flexibility of the teams controlling those distant machines. Multiple spacecraft orbit Mars, each designed for different scientific purposes, each answering to different mission teams. But in early October 2025, they all had a new priority. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter secured high-cadence observation slots for the critical week. Mars Express deployed its high-resolution stereo camera and Omega spectrometer to capture multispectral images and analyze chemical signatures from visible to infrared wavelengths. The Trace Gas Orbiter's Nomad and ACS spectrometers went even deeper, dissecting the comet's light into thousands of wavelengths, hunting for rare gases and molecular bands that could reveal its composition. The United Arab Emirates Hope Orbiter brought a different toolkit. Its EXI camera and EMS ultraviolet spectrometer, normally focused on Martian atmospheric science, were retasked to monitor this bright intruder. Hope's global orbit and flexible pointing made it perfect for wide field imaging and UV spectra, especially valuable if the comet suddenly flared. China's Tianwen-1, equipped with high and medium resolution imagers and a mineralogical spectrometer, could provide crucial context images and near-infrared spectra. Though official confirmation of its 3I Atlas campaign remained pending, the spacecraft had the capability. And then there's NASA's Mars Reconnaissance Orbiter, with its legendary HERES camera and CRISM spectrometer. MRO has a proven track record with Comet and asteroid campaigns. But here's where things get complicated. The US government shutdown meant that even if MRO collected data, public access became uncertain. Internal teams continued monitoring for spacecraft health and safety, but the usual flow of information to the scientific community slowed to a trickle. Together, these missions formed a layered observation network, each contributing a unique field of view and spectral range. Some results would arrive within days, others only after months of calibration and validation. The story of 3I Atlas would unfold in stages, each dataset a potential clue. While orbiters watched from above, something remarkable happened on the Martian surface. On October 2nd, NASA's Perseverance rover pointed its Mastcam-Z camera at the sky and held its gaze for 9 unbroken minutes. Each frame captured by the right Mastcam-Z came stamped with precise UTC timestamps and embedded metadata: exposure time, filter selection, camera orientation. The sequence was originally designed for routine sky surveys, but this time, something appeared, a streak cutting across the star trails, neither aligned with known satellites nor matching the slow drift of planets. The analysis that followed was meticulous. Raw images were run through calibration pipelines, flat-fielded, dark subtracted, corrected for bad pixels. Every artifact, every cosmic ray hit, every ghost reflection had to be hunted down and eliminated. Only after this rigorous process did the streak truly stand out, a faint, fast-moving line, consistent across multiple exposures. Astrometry took over. Analysts pulled NASA's PEACE kernels, the geometric toolkit that translates the rover's pointing into precise sky coordinates. They overlaid the predicted path of Three Eyes Atlas, derived from JPL's Horizons ephemeris system. The streak's angle and speed matched almost perfectly, nearly 400 arc-seconds, aligning with the comet's projected motion as seen from Jezero crater at that exact hour. But science demands more than coincidence. False positives had to be eliminated systematically. Cosmic rays leave sharp, single-pixel scars, not long continuous tracks. Internal reflections repeat with camera movement, but this streak held steady. The team applied median filters and sigma clipping to weed out transients. They measured flux along the streak's length, checking for any sign of flaring or fading that would betray a camera glitch or dust interference. The photometry looked good. The streak was faint but persistent, its brightness profile matching what a diffuse, fast-moving coma would produce at Mars's distance. The light curve was flat, no spikes, no sudden drops. The final test was the fit. The streak's measured position was plotted against the predicted ephemeris for Three Eyes Atlas. The residuals, the differences between expected and observed, fell within just a few arc-seconds, well inside the margin of error. If confirmed, this would be the first direct detection of an interstellar object from the surface of another planet. But the US government shutdown left JPL's instrument leads silent, their review on hold. Independent analysts published their findings, but the official chain of verification waits for NASA's endorsement. The streak is there, burned into 9 minutes of Martian sky. What happens next will determine whether it becomes a landmark detection or a cautionary tale. On September 25th, a single amateur observatory in Namibia captured what would become the last clear portrait of Three Eyes Atlas before Earth's observation window slammed shut. The image, taken under southern skies just hours before the comet slipped into solar conjunction, revealed something extraordinary. The emerald coma stretched nearly 700,000 kilometers across, almost twice the distance from Earth to the Moon. The core glowed vivid green, a hue that immediately set it apart from typical solar system comets. This color came from sunlight filtering through diatomic carbon and other gases, scattering in a way that produced an almost unnatural glow. But the structure was stranger still. Instead of the long, trailing dust tail we expect from textbook comets, Three Eyes Atlas displayed a sunward antic-tail, a wedge of material pointing toward the sun, not away from it. This bizarre feature, shaped by large, slow, moving grains and the peculiar geometry of its interstellar trajectory, gave the comet the appearance of a drifting fan rather than a classic streak. Fainter shells and arcs rippled outward from the nucleus, suggesting episodic ejection events rather than a steady, wind-blown stream. Follow-up image stacks from September 27th and October 2nd, though noisier and hampered by increasing solar glare, confirmed the pattern. The coma's boundaries held their shape even as the object faded, resisting the smearing and elongation expected from typical dust-driven tails. These snapshots, collected in the last days before Earth's enforced blindness, now serve as the baseline for everything Mars would see next. The data behind Three Eyes Atlas refuses to fit any familiar pattern. Start with velocity. Most long-period comets entering our solar system travel at 20 or 30 kilometers per second. Three Eyes Atlas rose past Mars at nearly 60 kilometers per second. By the time it sweeps through perihelion at the end of October, Models project it will spike to 68 kilometers per second, a speed that leaves even the fastest solar system comets in the dust. The trajectory is equally strange. Instead of plunging in from some steep, random angle, the signature of objects from the Oort cloud, 3i Atlas hugs the ecliptic. Its inclination sits barely a few degrees off the plane of the planets. For a true interstellar visitor, that's statistically rare. Most are expected to arrive from high, tilted orbits, not slip in almost unnoticed along the solar system's own highway. Size presents another puzzle. Early brightness estimates paired with Comet models point to a nucleus at least 5 kilometers across, possibly larger. That places it among the largest interstellar bodies ever observed, rivaling 2i Borisov and absolutely dwarfing 1i Oumuamua. But the Comet itself is the most confounding feature. Polarization studies hint at concentric shells or arcs, each reflecting light in subtly different ways. There's no long filamentous tail, just a massive, structured cloud that defies standard comet physics. For dynamical modelers and planetary scientists, each data point presents a fresh challenge. The usual playbook offers few answers. On September 25th, 3i Atlas faced a different kind of test, a coronal mass ejection hurled straight from the Sun. Space weather forecasters tracked the CME as it swept through interplanetary space, predicting a surge of charged particles and magnetic turbulence. For most comets, this kind of solar blast is a recipe for chaos. The sudden arrival of energetic plasma strips ions from the coma, triggers rapid outgassing, and can sculpt entirely new tails within hours. Scientists at plasma laboratories and solar observatories expected a textbook response, a shock front, a burst of ionized gas, maybe even a visible kink in the comet's envelope. But what actually happened was almost nothing. As the CME enveloped 3i Atlas, ground-based telescopes and Mars-side instruments tracked the aftermath. Instead of a dramatic flare, up or reshaped coma, the comet's structure barely shifted. The green halo stayed crisp. The antitail held its wedge-like form. The outer shells showed no sign of sudden expansion or fragmentation. For plasma physicists, this muted response is deeply puzzling. The expectation was clear: more ionization, a swollen envelope, at least a hint of magnetic turbulence written into the comet's light. The absence of a strong reaction raises fundamental questions about the object's composition and internal structure. Is the coma unusually resilient? Or is there something about its chemistry that naturally resists solar weather? Without a clear ion tail or a burst of emission lines, the usual diagnostic tools come up short. Researchers now look to Mars orbiter plasma instruments and high-cadence spectra for answers, hoping that somewhere in the raw telemetry, the fingerprints of that solar storm are hidden, waiting to be found. The orbit of 3i Atlas leaves no doubt about its origin. Its path cuts through the solar system on a hyperbolic trajectory, unbound, never to return. This mathematical fingerprint confirms interstellar travel, placing it in rare company alongside 1i Oumuamua and 2i Borisov. But certainty about origin is only the starting point. The real debate is about what to call it and how to interpret what we're seeing. Some researchers reach for the familiar label, interstellar comet. They point to the green coma, the outgassing, the layered envelope. Others hesitate, citing the missing dust tail, the bizarre anti-tail, the stubbornly stable structure, and that almost mechanical velocity. This debate isn't just academic terminology, it's about evidence and the standards we hold for extraordinary claims. Science advances through skepticism by asking not just what fits our expectations, but what survives the next round of scrutiny. The lessons of Oumuamua remain fresh. Models multiplied. Speculation raced ahead of the data. But in the end, only the hard measurements endured. For 3i Atlas, every anomaly, every odd color, every mysterious shell, every unexplained behavior must be tested rigorously, not hyped prematurely. The question isn't whether it could be something extraordinary. The question is whether any measurement compels that conclusion. Until then, the only certainty is its interstellar passport. Everything else remains hypothesis, waiting for the next spectrum, the next image, the next surprise. On October 3, 2025, 3i Atlas passed just 30 million kilometers from Mars, while Earth-based observatories remained blind, victims of solar geometry and governmental shutdown. Mars orbiters from Europe, The UAE, China, and the United States became the sole witnesses, capturing data unavailable from anywhere else in the solar system. Early results confirmed a green coma over 700,000 kilometers wide and a blistering speed near 60 kilometers per second. But key questions persist. What is the true composition of Three-Eyed Atlas? Why does it display that layered coma structure? Where is the classic dust tail? And why did a direct hit from a solar CME produce so little visible effect? As international teams process their findings and prepare for staggered data releases over the coming months, much remains unexplained. The confirmed interstellar origin of Three-Eyed Atlas is not in doubt, but its nature challenges every comet model we have. For now, the machines orbiting Mars hold the only complete record of this encounter. They watched when Earth could not. They captured what might have been lost forever. And as their data streams back to Earth, piece by piece, we're reminded of a humbling truth. Even with our global network of telescopes and spacecraft, even with our best instruments and brightest minds, some cosmic mysteries endure. The story of Three-Eyed Atlas is unfinished, and that's exactly how science should be. Filled with questions worth pursuing, mysteries worth solving, and data still waiting to reveal its secrets. If you want to follow the unfolding story of Three-Eyed Atlas, check the description below for links to ESA's Planetary Science Archive, the UAE Hope Mission Data Center, and community analysis forums where independent researchers are tracking every new release. This is science happening in real time, and you can watch it unfold.